Thompson sampling is another very popular class of algorithm, which is Bayesian approach. Okay, there is prior distribution. There are some prior distribution on hidden parameters, and after each observation, we update the posterior distribution for each hidden parameters, and using the posterior distribution, we choose a new action. Okay, for instance, for this Bernoulli bandit, people usually assume uniform prior, and then update hidden parameter using posterior. In that case, because every observation is Bernoulli, the parameter becomes beta distribution using some theory. So Thompson sampling is a randomized Bayesian algorithm. So that sample hidden parameter using posterior. So just randomly sample hidden parameter. Okay? Essentially all the hidden parameters. So we first consider mu1, mu2, everything follow uniform distribution. So mu1 can be from 0 to 1 with equal probability, mu2 as well. When we play one of the arm, one of action, then we observe 0 or 1. And based on 0 or 1, we update the distribution of mu2 using beta distribution. So there is some update of posterior distribution after a few number of observation. And then every time slot, how can we utilize such posterior distribution? Just randomly sample one of value from the posterior distribution and then compare them. Draw AT having the largest sampled value. Okay, just a mu t, we sample mu t from the posterior and pick the arm having the largest sampled hidden parameter. This is called Thompson sampling. One nice thing of Thompson sampling is when we can approximate the posterior distribution, the simple random sampling based on the posterior distribution can give us very nice algorithm. For instance, this paper tells us this Thompson sampling is asymptotically optimal, so means this Thompson sampling also achieved the optimal reward performance like a KL UCB. So for instance, in this case, again, based on the observations, we can update the posterior distribution, and the posterior distribution having high variance when the number of observation is small, having very tiny variance when the number of observation is large. And from this distribution, we randomly sample one of our values. So when we have high variance distribution, then with some chance its value can be very large, which encourages exploration. And also the posterior distribution memorize some past information using the expected value. So when we have many positive outcomes, then naturally the distribution having high expected value, high mean value, which naturally make some exploitation, which we will more frequently having largest value using higher posterior, higher mean posterior distribution. So the Thompson sampling can give us very nice exploration and exploitation trade-off. Right. So up to now, we have discussed multi-arm bandit, where we want to balance the exploration and exploitation trade-off. We want to visit many arms several times to understand hidden parameters accurately. But in the meantime, we also want to exploit the hidden information, observe the information so that the expected return can be maximized. Another possible goal is just pure exploration objective. So we have a capital T number of budget, and after capital T number of budget, we want to find the best sum with most accurate way. So which means we don't care the trajectory, we don't care the rewards during the capital T exploration. We just want to find out the best policy just after capital T number of plays. Okay, we don't care how badly you behave during the capital T number of observations. We just want to the final outcome that having the true, that having the best solution. It also has many applications. For instance, when you train AlphaGo algorithm, we don't care the middle time algorithm performance. We just have some limited computation resource and limited budget. So during that time, we just want to find out one single algorithm having the best return. Okay, that is another pure exploration application. Okay, so but the algorithm philosophy almost the same. LUCB turns out kind of optimal. So here, for the pure exploration, we care not only the upper confidence bound, but also lower confidence bound as well, to remove very unlikely optimal samples. Okay, for instance, if one arm's observation is always zeros, then after some time, we know that this arm very rare has very rare chance to win. So we can save some sampling budget for that very bad arms. You know, during the exploration, we can know some arms is already very far from the optimal. For that case, because we can very easily discriminate them, we can save some sampling budget and save sample budget. We can use the saved sample budget to more confusing arms. Okay.